So I would like to introduce Abigail Ward as our first speaker today from Harvard University. And she will be speaking on homological mirror symmetry for elliptic Hopf surfaces. So without further ado, go ahead.
All right, thanks. Okay, let me first figure out how I can share the screen. Wait, so how do you do that again? I forget the step on Zoom.
There's a green box at the bottom of your screen if you hover over it.
Oh, I see. Yeah. Thanks, Joe. Yeah. Okay. Okay. Okay, sorry, 1 second, guys. This is a new iPad for me. Okay. So, yeah, so can everyone see that title slide? Yes. All right, so sorry about that. Yeah, so first of all, thank you very much to the organizers for the invitation to speak. It's really cool to get to do this in this format. It's a really good way to sort of have an excuse to retire a talk after an entire world gets to see it. So happy to do that. All right, so as Catherine said, I'm going to be speaking about homological mirror symmetry for elliptic Hopf surfaces. So just to give you a sort of outline of the talk, the first thing I'll do is just sort of remind people what homological mirror symmetry is through examples. So I'll be doing HMS just very, very briefly for P1 and the elliptic curve. And then I'll then move on to talking about what these elliptic Hopf surfaces are. So section 1 is about Hopf surfaces and sort of their properties that we'll use. And then 2 is going to be sort of the mirror side, so defining so the non-algebraic Landau-Ginzburg models that I mentioned in the abstract. And then 3 is going to be the mirror symmetry results. So sections 0 and 3 are going to be fairly examples-based mirror symmetry. So the goal, or maybe a motivating question, is how does HMS extend beyond the world of Kähler manifolds? So for what spaces can we find like mirrors? So what is homological mirror symmetry? So this was a conjecture of Kontsevich in 94. And I ask if you're listening to the talk in my living room that you put on headphones, because it's disconcerting to have the echo. Sorry, guys. I have roommates interested in this as well. Okay, so this was a conjecture of Kontsevich in 94. And he said, okay, physicists had been observing a bunch of these mirror pairs. He said that there's some sort of deeper categorical sort of formalism sort of underpinning all of this. The conjecture is that Kähler spaces compare to XYs, and there are equivalences between like the derived category of X and the Fukaya category of Y, and vice versa. So for these sort of equivalences, you'd expect something like, okay, so your objects in the coherent of DB-Co or something like coherent sheaves. This is a very loose sort of correspondence I'm going to write down here. So coherent sheaves on X can correspond to Lagrangians in Y. then you would expect, okay, so the morphisms here are given by X groups of sheaves, and then these are sort of going to correspond to Floor cohomology groups, whatever. And then your native, so then, given two sections of a sheaf or something, you can multiply them. And in general, you have this Unita project on X groups. So the Unita products on this side are going to correspond to sort of counts of holomorphic disks in Y. So on the left-hand side here is my complex side, and the right-hand side is the symplectic side. And then one of the first concrete examples was done by Paul Zaslow in '94. I think that might be wrong. I think it might be '96. So they did the case of the elliptic curve. So I have this EQ. So what this is going to mean is always C star and mod the Z action by scaling. So Z gets identified with QZ, and then here Q is something in C star that has norm less than 1. And then this is identified, this is mirror to sort of the same, the same underlying space, but with a symplectic structure. This is mirror to the torus with the complexified Kähler parameter. Q. So if Q is in R, you just want to think about this as the torus with area Q. And then the correspondence here, so coherent sheaves on the elliptic curve, you can understand in terms of sort of their rank and their degree. So line bundles are rank 1, degree D. And sorry, this doesn't make any sense. Lines of rank R degree D, I should be lines of slope D over R, sorry about that. So, but as this said, corrected, coherent sheaves of rank R degree D correspond to lines in this torus with this specified sort of topology. And then I put plus decorations because then you want to equip them with maybe vector bundles and connections. And then you see that the counts of the J holomorphic triangles on the symplectic side here correspond to or recover the sort of classical theta function identities. And so this is a paper by Paul Zaslow. So just to sort of give you a quick sort of idea of the kind of things that you're looking at here. So right, that the Jacobian of the curve, or if you'd like the degree 0 line bundles on the elliptic curve is, isomorphic to the curve itself. So you have a sort of torus family of line bundles. And then, so these objects here are going to correspond to these lines, so lines of slope 0. So then you might be unhappy because it seems like there's only a one real dimensional family of those plus, but then you say, okay, but I want to add in these unitary flat connections. So plus unitary flat connections. And then you can kind of see that this space forms a torus. So this gives you torus in your sort of Fukaya category of EQ. Okay, so that's kind of the simplest case. So let me just say that, yeah, let's note that in this case, the first Chern, this is the Calabi-Yau case. So the first Chern class of this thing equal to 0. If you want to move beyond the Calabi-Yau case, maybe a simple way to see that is, or a natural thing to look at is CP1, the complex projective plane. and people say, okay, so the complex projective plane CP1 is mirror to this pair of C star with the function Z plus 1 over Z. And this is what people call a Landau-Ginzburg model. And to this Landau-Ginzburg model, we can associate like a Fukaya sidal category. So that's this thing. Sorry, so this should be C star here. So that's this thing. So the objects are equal to, say, Lagrangians in C star, that fiber over the positive real axis. And then the morphisms are computed by, this is very, very loose, pushing off at the end. So you're allowed to have sort of non-compact Lagrangians, but they have to go off to infinity sort of in a specified way. So if instead of thinking of C star as C star, or instead of using like a complex coordinate there, so fiber over R equals 0 under W, I should say that, and then this is your superpotential W. What did I want to say? Yeah, so an example of such an object might be if I say, just like define a Lagrangian Ln, and this is if you sort of see C star as a cylinder here, you want to think of something that sort of wraps n times. So maybe something that kind of looks like this. Sorry, I apologize. I'm probably wrapping in like the wrong direction. But okay, so this would wrap 2 times. So this is L2. And if I want to write these in coordinates, so if I switch these T phi2 coordinates on R times S1, so now my symplectic form would just be like a dt wedge d phi t, then this condition on the fibering over R is greater than 0. Well, you can think of it at the ends as, okay, so when you get to very large Z, this term this superpotential is going to be equal to this. Very small t, so t greater than 0 dominates, and then similarly for the 1 over Z dominates on the other end. And these conditions can just kind of be thought as phi t, the angular coordinate there, goes to 0 as t goes to infinity. Absolute value of t goes to infinity, right? And that sort of encapsulates this this idea that you have to sort of fiber over this real axis. So then in these coordinates, I could write Ln as something that looks like kind of the set of such things. T, sorry. I promise, I have a reason I'm doing all of this. I'm going to come back to this later. So T, and then sort of the graph of some function negative n times rho of t, so for t is in R, and then rho of t is going to be just a function that's equal to some sort of smooth kind of thing that approximates a step function. And then under this correspondence, this is going to be mirror to the line bundle O of n. So one sort of remark I want to make is that this is sort of like a baby example of the sort of philosophy of performing HMS like in the complement of an anti-canonical divisor. And the full power of this, you can see in this paper of Aru of the same title. The idea is like maybe you start with something which is some sort of open Calabi-Yau. So if you take over a projective variety and then take away its anti-canonical divisor, so you can often find a mirror to that, maybe using SYZ mirror symmetry or something. This is really for the experts, these comments. And then I can compactify like by adding back in the anti-canonical divisor, and then this is going to be sort of equivalent to equipping the mirror side with some superpotential that counts sort of Maslov index 2 disks passing through the anti-canonical divisor. So that's a philosophy that's sort of useful to keep in mind throughout, like if you know it, but it's not going to like logically function in the talk. All right, so that's sort of the preface to the talk. Okay, so now I want to introduce the complex space I'm going to be considering, which is the Hopf surface. So the Hopf surface is given by I have it written here. So it's if you take the quotient of sort of C2, punctured C2 by a Z action. So Z just acts by scaling. So again, I'm just going to say, okay, so I should have a complex parameter Q in here. And then again, Q is just some complex number with norm less than 1. So you can kind of check for yourself if the norm of Q is 1, then you could have like very weird sort of topology here. But if the norm of Q is less than 1, then Z acts freely on this sort of punctured C2. And if you take the quotient by that action, you get actually something which is diffeomorphic to S1 times S3. So some properties of this surface I'm going to use. So it's elliptic. So first of all, so what I mean by that, so there's a map from SQ to P1. And then in coordinates, it's just given by Z1, Z2, maps to Z1, sort of the ratio of Z1 and Z2, right? So if you like on the S3 factor, that's just the Hopf vibration. What I want to say about that, and then the fibers are all the same elliptic curve. The fibers are the elliptic curves E sub Q. So that was my elliptic curve with complex parameter Q. Okay, so this thing is projective, but not Kähler. This is easy, right? Because the first Betti number is 1. And then the other property I want to note of this thing is that if you take away the sort of elliptic curves that you get by quotienting the sort of coordinate axes, so the Z1 equals 0 axis, Z2 equals 0 axis. So first of all, so the union of those two axes is anti-canonical, and if you take it away, you get some sort of open Calabi-Yau surface, right? So you get some C star times EQ. So what this is actually doing is this is like, this equality here is like some sort of trivialization. Maybe I just want to call this map pi. I don't think I'm ever going to use it again now. Trivialization of pi away from poles of P1. Okay, and then just a little sidebar. So terminology. If you have, if G is a discrete group, and then G acts freely on C squared minus 0, then the quotient C squared minus 0, sorry, that's, yeah, mod G is a Hopf surface. So a Hopf surface. And then this SQ is sort of the classical Hopf surface. So it's sort of the prototypical one, but you actually have sort of a whole family of them. And I'm going to deal with some of them in this talk. So, okay, so the next sort of slide is a little bit of a detour, but I did put up my abstract, so I want to mention it. Hopf surface actually can be thought of, okay, so you can get this as quotienting C, but maybe it looks kind of like ad hoc or kind of like a coincidence. But in fact, this actually kind of fits into something we do understand fairly well through sort of knowing about the complex geometry of elliptic surfaces. So, so given an elliptic surface x over b, so again, just some complex surface, and a smooth fiber xb over b, you can perform this logarithmic transformation, which is topologically just some sort of surgery, to obtain a new elliptic surface that also fibers over b. This thing has parameters mk, so this is some pair of integers, so I'm going to say it's in Z2, and then it has the conditions that m is not equal to 0. Actually, I want to say m is positive. And then this is a primitive vector in Z squared. So you can have 1, 2, but you can't have like 2, 2. Okay, so you get a new elliptic surface, x prime also fibering over b, and then the key fact is that these two things have the property that away from these sort of fibers, there's a biholomorphism from x minus xb to x prime minus xb prime, so biholomorphism. But this is not a birational move. So if you're, if you're an algebraic geometer, you'd be tempted to say like, okay, well, I know it's a biholomorphism away from a codimension one set, biholomorphic, or it's a birational thing, but it's very much not. So this thing can really kind of radically change some of the complex geometry of your thing. So it can change the Kodaira dimension, for example. Or more dramatically, it can kind of change whether this thing is an algebraic surface or not. So what I want to do is I want to say, take P1 times E. So let's say EQ. Okay, so I think I've dropped the Q like throughout this talk, but just whenever you see like some sort of these surfaces S, there should be there's sort of an implicit Q, which is this complex parameter. So I'll put it in here just so you can kind of see how that would work. Okay, so I want to take this P1 times EQ, and then I can perform some logarithmic transformations over 0 and infinity. So I need two kind of, I guess you would say vectors in Z squared to do that. And I'm going to index them. So M0, K0, so that's the parameters that give you the logarithmic transformation over 0. M infinity, K infinity, that gives you the logarithmic, the parameters over infinity. And then it's a fact that the classical Hopf surface S, so this is classical Hopf, is equal to this thing in the case where the parameters are 1, 0, 1, negative 1. So 1, 0, I didn't tell you this, but that's a trivial move. So you're just performing one logarithmic transformation over infinity. And then sort of by design, if you take away, so by design, there's a biholomorphism away from the fibers that you sort of did this move at, right? So C star times E embeds into S, this S of A, and I want to say like S of A minus C star times E. So this is some divisor. This is anti-canonical. And then I probably want to say with its reduced scheme structure. So the goal is to understand mirror symmetry for these surfaces. So to find a symplectic space and an associated Fukaya category, so that so coherent analytic sheaves, which really you should just kind of think about as sort of holomorphic vector bundles. Like that's fine if you just think about that. There's still a notion of holomorphic vector bundles is the point. Correspond to, so let's call my space Y and an associated Fukaya category f of Y. So I want to say, okay, coherent analytic sheaves on this complex space correspond to objects of this Fukaya category. Okay, so let me just pause a little bit. So what I want to note here is that, or what I want to kind of say is that if you think back to this sort of idea of performing mirror symmetry relative to an entire canonical divisor, like this is a fairly natural thing to do, right? Because I have this sort of so away from an intercanonical divisor of all these surfaces, I have this space C star times E, and I can hope to understand mirror symmetry for that space. I guess I didn't say this, but you kind of expect that mirror symmetry commutes with products. So you sort of have a potential mirror to this guy, and now you want to say, you know, if I was doing mirror symmetry for P1 times E, I could just kind of compactify by adding in Landau-Ginzburg superpotential. I get boundary conditions on my Lagrangians at infinity. Maybe I kind of hope to do the same thing here. And that's sort of indeed what we're going to do. But let me just first convince you that this is an interesting thing to study at all, the complex geometry of this Hopf surface, by talking a little bit about analytic line bundles on the surface. So I want to think, or sorry, holomorphic line bundles on S. So holomorphic. So it's a fact. So here S is just my Hopf surface again. So it's a fact that the analytic Picard group of this space S is given by C star. I'm going to write this identification. So lambda and C star maps to a line bundle L lambda. And then the total space of L lambda, sorry, curly L, is going to be equal to something, so C squared minus 0. And now I have a C kind of tacked on, and now we're going to quotient by, so vector, I'll use vector notation for my things in my C star, C squared minus 0, so ZT gets identified with QZ lambda T. So this is just a natural thing to do if I said, okay, well, given a representation of the fundamental group of your surface, how would I build a holomorphic line bundle on it, right? So you know how to do that, and you get this sort of, you would get a map from this Hom group into your analytic Picard group. Oops, sorry, skipping ahead. And then a fact, which you can check, is that that map is actually an isomorphism. What do I want to say? Okay, so you expect there to be some interesting holomorphic line bundles on this, because on S, because you can pull back line bundles from P1, right? So one thing I want to note is that when L, maybe I'll say, so L of Q to the N is equal to the pullback under that elliptic vibration map of O of N. Okay, and then I can say, well, how do these things interact with each other? So it turns out you can calculate sort of the X groups of these line bundles. So they're line bundles, so the sort of X group is really just like some sort of sheaf cohomology. And you see that if your line bundle that you were computing the sheaf. So that's what I'm saying. It's sheaf cohomology of this thing. So this, or rather this, cohomology group. If you pulled back a line bundle from P1, then that line bundle will have interesting cohomology. So you get a copy of its cohomology from P1, and then you tensor, this is just like some sort of shorthand, you tensor just with the cohomology of S1. So something in degree 0, something in degree 1. You can calculate this with any sort of, you can use like Serre duality and Grothendieck Riemann Roch. You still have some tools, even if though you're not in a projective world, you still have some tools to sort of do calculations like that. And then if the line bundle is not pulled back from P1, then its cohomology is 0. So you sort of have this like Z sort of lattice of line bundles with interesting cohomology sitting inside your analytic group, which is some C star. Okay. So that's nice because it kind of gives us objects we might want to find mirrors to. Remember, like I exhibited like Lagrangians, which were mirror to line bundles on the elliptic curve in P1, and now we have some collection of line bundles we might hope to do mirror symmetry with. So that's good. Okay, moving right along to, okay, well, maybe I'll pause because I'm actually doing pretty well schedule-wise. So are there any questions? Okay. So feel free to interrupt me at any time, like if there are. But I want to get to the actual symplectic geometry of the talk. So this is these so-called non-algebraic Landau-Ginzburg models. Okay. So I promise now I'll slow down a little tiny bit. So for the rest of the talk, I'm going to consider the symplectic space Y. So this is just going to be equal to R times T3. And I write it in coordinates. R times S1 times S1, coordinates T, S, phi T, phi S. And with the symplectic form, dt wedge d phi T plus ds wedge d phi S. So you can kind of think about this as sort of equal to C star times E with sort of its standard symplectic form, right? Normalized so that the symplectic area of the elliptic curve factor there is 1. Okay, what do I want to say about that? Maybe not much more. That's a pretty easy space, except that, okay, so this C star times E is what you would say the SYZ mirror to sort of itself. Oh, here, maybe I'll write the. So that would be sort of the space we were going to be starting out anyway, if we were going to do this like relative to an anti-canonical thing. If we were going to follow that heuristic. And then A is going to be some set of indices, M0, K0, M infinity, K infinity. Okay, and so you can kind of guess at the punchline already maybe, but what I want to say is that so these things have the same properties as like sort of the parameters for our log transforms we did before. So yeah.
You have a question from Augustine.
Oh, okay, yeah. Hi, Augustine. What's up? Do you wanna unmute yourself, or do you wanna? I can read the question.
Hey, Abby.
Hey.
No, just briefly. Can you briefly remind me of what the log transformation is doing? At least I don't know topologically or something. You said something about a surgery.
Yeah. So. So topologically, let me sort of put in a new page. So topologically, so if I have a surface S, and say it's just over a base B, and I have, I want to find a sort of neighborhood of the fiber XB. So I have U sort of sitting inside of S, and then this is equal, like I guess smoothly to XB, but just sort of not as a complex, and this is not an isomorphism of complex spaces, but times a little disk d. This is just errors in terms, like you can just trivialize a fibration of a smooth fiber. So this is inside of C. And then what I want to do is that, so like the boundary of this thing, if I'm not mistaken, is equal to T3, and then you perform a surgery along this T3. So you remove this U, and then you kind of glue back in a sort of solid torus, but you're going to change the boundary a little bit. The complex model that's sort of useful is that if I write, well, okay, maybe I'll just leave that there because I think that answers your question. But at the end of the talk, I'm also happy to talk about like what the actual model is.
Sure, thanks.
Yeah. Okay. All right. So now let's go back to this thing. Thanks, Augustine. I'm glad you asked that. Okay. So the non-algebraic Landau-Ginzburg models. Yeah. So got the space, these indices. So these are two things in Z2. Z squared with the properties I said before. So primitive and m naught is greater than 0, m infinity is greater than 0. And now I want to consider some Lagrangians in this space Y that sort of obey some nice boundary behavior at the boundary with respect to these boundary conditions. So I want to say at one end, when t is much less than 0, or okay, sorry, oops, this is oh no, my pencil is running low on battery. When I give the theorem, I'll just like pause and not use it for a bit. So at one end, so when t is much less than 0, I'm going to say the Lagrangian, this function m naught phi t plus k naught phi s is identically equal to 0 on the Lagrangian. So you should really think about this like in R mod z, whatever. And then on the other end, you have a similar sort of condition, but with the other parameters. Okay, so what's happening here is that, okay, and then nice is like, so well-behaved Floer theory. So I don't want them to bound disks, for example. I actually need a lot of conditions on them, but they just to make the Floer theory well-behaved. So a picture is like, okay, so here's sort of Y, here's sort of L sitting inside of Y, whatever. And then at the ends, oops. So I can project down to, this is the phi t phi s torus. So this is some pi phi t phi s. So this is the projection for L with t much less than 0. So that this is going to project over some sort of line, like maybe this. So this would be in the case that m naught k naught equal to 1, 1. But I wanted to say, okay, so if you know about sort of Landau-Ginzburg models, so I'm going to say this is a Lagrangian projection, right? This is not like some sort of superpotential here. This is a Lagrangian plane, the phi t phi s plane. Okay. So now I'm going to define a Fukaya category that has objects being these things. So the objects of my Fukaya category are going to be given by again, sort of the Lagrangians in the set GA, morphisms are going to be given by perturbing the Hamiltonian at the ends. So the picture here is that, so I want to say you flow one of your Lagrangians by a Hamiltonian with H naught is equal to epsilon absolute value of t for absolute value of t goes to infinity, and then epsilon is less than 1 over m, 0, and also less than 1 over m infinity. So what's happening here is that, so again, if you look at this phi t, phi s torus, if I say, okay, I have one Lagrangian L naught, one Lagrangian L1, so L0, so this has the effect of, this flowing by this Hamiltonian has the effect of pushing phi t up. So now this thing, you know, previously lived in that diagonal line, now it's going to live slightly above it. And then, you know, my other guy unperturbed still lives in that line. I guess. And you can see that these are going to be disjoint at infinity. So your flow complexes here are actually sort of finite dimensional you know, modules. And then your structure products MK. So I should say, okay, so this is some A infinity category over the Novikov ring lambda. And then MK does sort of the standard thing where, so you say MK of yk minus 1 dot 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 y0 is going to count sort of disks with the correct boundary conditions. So it's going to count number of points in some moduli space, which just looks like sort of holomorphic maps from your disk into your space, which sort of send boundary mark points to these guys, right? So yk minus 1, and then this is y out. Yeah, so you count these J holomorphic triangle or disks, and then you weight the output by the holomorphic area, or sorry, the symplectic area of those disks. So fairly standard thing, except now I've sort of twisted the boundary conditions at the ends. Okay, and then I also define some wrapped and partially wrapped categories. So again, so this is a little bit more for people who have kind of seen wrapped and partially wrapped categories before. So the partially wrapped is sort of, I relax the boundary conditions on one end. So I'm going to call that like this FMK. This is a sort of thing where I've said, okay, you're going to take all the Lagrangians. I mean, I've kind of written it sort of, you know, cheekily there. It's just saying, well, just take the union over all the Lagrangians that sort of have the m prime, k prime, you know, whatever other linear boundary conditions at the other end, but they obey the mk boundary conditions at the t much less than 0 end. The fully wrapped category is like you just take the set of all linear Lagrangians that obey any boundary condition. So this is some sort of like much larger space of Lagrangians. Okay, and then to compute the morphisms, you wrap at ends with relaxed conditions. Sorry, my handwriting is not so great. So what does this mean is basically you want to take perturbed by Hamiltonians, which are equal to some sort of quadratic thing at the wrapping end, and still equals to epsilon times the absolute value of t at the other end. And then actually they sort of form a system. And one way to say it is that the Homs is going to be the direct limit of these things.
Oh, Abigail?
Yeah.
I think if you just wrote something, it didn't show up.
Oh, damn. Okay. Let me try to like
Maybe unshare and reshare.
Yeah.
All right.
Sorry, that's happened before, but I thought it had stopped.
Oh, there it
Thank
is.
you so much. Yeah. Thank you so much. Yeah. Okay. Well, fortunately, I didn't really write anything except for rapid ends with Roux conditions, and correct my absolute values of these there. Okay, and then one more thing I should say is that I mean, actually, this is all through some sort of categorical localization procedure through that unpublished work of Abu Zaid and Seidel, but since found in Ganatrapart and Shinde, and work of Ganatrapart and Shinde and other places as well. So take everything on this page with a grain of salt. But the last thing I want to say is that so these two Lagrangians have infinitely many intersection points. And so I need to complete the Floer complex. So this is some completion. That's what I mean by this hat. So I'm allowing sums. Normally, like when you do some sort of Fukaya category, even if you have infinitely many intersection points, you still have some sort of a priori bounds on sort of the outputs of any sort of disk you consider. So actually, it suffices to consider finite sums instead of like kind of finite sums of intersection points is closed under your flow products. Here we don't have that. We don't have a priori control over the outputs of our disks. So we have to actually do a completion. And this is also kind of why I want to do the wrapping first, as opposed to sort of taking the direct limit over maybe linear and Hamiltonians. What else do I want to say?
You have a question from Hiro.
Yeah, go ahead, Hiro. But I'm not going to be able to answer your question if it's from you, Hiro. I don't know enough.
Well, let's see. Well, so you said that you have to complete all these home complexes.
Mm-hmm.
So, if you're not completing, then I know what an MK operation is. It's a map from a K-fold tensor product of the home complexes to an output. But how worried should I be about the kinds of tensor products you're taking now to define the MKs?
I don't think you should worry about the tensor product. I mean, basically, I just extend. That's a good question that I don't think the difficulty there is in sort of doing the algebraic formalism. So if I have some sort of set, I don't want to write this down, so it's gonna be a huge mess. But if I have just sort of objects which you can kind of think about as infinite sums of power series sort of, then I can just sort of extend linearly. So what I mean is just like if I want to take like M2 of sum of C alpha, Y alpha, sum of
I see. So you just need to check a convergence property.
Yeah, exactly. Yeah. But I'll write this down because I think it was probably confusing. Is just going to be equal to the sum, alpha beta of M2, Y alpha, Y beta, and then weighted by C alpha.
And to be clear, you're taking a completion with respect to something non-Archimedean. You're not using
a non-Archimedean thing. Yeah. Basically, what I want to say is really simple. It's just like your Novikov valuation of your C alphas. So val C alpha goes to infinity. To work over C, I would need some sort of more different sort of completion, which does appear. But for now, I just want to think about you're allowed to sort of have infinite power series, but then your T coefficient goes to infinity.
So after you take the colimit, do you complete again?
No,
Oh,
I don't think so.
okay. Thank you.
Like, I can really say like these things sort of stabilize, and I can really say I can complete the Homs from sort of these groups, like sort of from the like individual sort of polar complexes. But maybe let me come back to this at the end because I'm like running a little bit short on time.
Sorry.
And I'm gonna get no, you're good. Thank you so much for the questions. This is sort of the a lot of the meat of the work. And then the other thing is just I have localization maps here between these categories. So if I have a Lagrangian in f of A, in fact, I can think of it as that Lagrangian also gives you an object of the wrapped category, the partially wrapped category. So this is A is equal to M not K not MK for some MK, it doesn't really matter. Then it localizes to live in this M not K not partially wrapped category. Okay, so Mear theories mean statements. So the first theorem is about Mear symmetry for the closed surfaces. So if I say, so first of all, I mean, this is not a theorem by me, but this part. But when you're a determinant, so whether or not you get an algebraic surface when you do these sort of log transforms is kind of determined by whether or not the two parameters are sort of collinear once you swap a sign. So if they're not collinear once you swap the sign, if the determinant of this matrix is not equal to 0, then your surface is elliptic, an elliptic Hopf surface, sorry. And the first theorem is that for such A, there's a full and faithful functor from the category, this category, which is I've just written as like this analytic Picard group, which has objects sort of equal to, objects or the line bundles morphisms are given by sheaf cohomologies. So full and faithful from that category to this category, which is the cohomology category of the Fukaya category of sections, which I have written sort of in that top right-hand corner. And then you're evaluating, so this would be an SQ, and then you evaluate your Nabokov parameter. So this is this evaluation sub Q map. So this sends evaluation sub Q of C alpha Y. Maybe I want to say like, T to the alpha Y to Q to the alpha Y. So this is just something, a category over, so this is some sort of category over C. You have to check convergence. And what I want to say is like, this is kind of an equivalence once you sort of impose the right sort of restrictions on your decorations of your Lagrangians. But note, so this is not enough to prove a full HMS statement.
I think you might need to reshare. It's not showing up again. Sorry.
Okay. No, I'm sorry, I don't know. Okay. So this is not enough for a full HMS. Instead, you might want to hope to use the following theorem, which says that all these partially wrapped categories and so on play well with each other. So this is just some sort of technical thing where I'm defining some sort of subcategories of categories of line bundles on your sort of open surfaces. So recall that we had sort of like a C star times EQ sitting inside of each SA. What I want to say is, okay, think about analytic line bundles which can extend to some such compactification of C star times EQ. You don't want to consider all holomorphic line bundles because that's just way, way too big of a set. But if you think of ones that can extend to some compactification that we've considered, that's actually an okay kind of subcategory of this Picard category. And then similarly, okay, so the next one's kind of written terribly. But basically it's like, okay, if you consider sort of a partial compactification of your C star times E in this way, where you sort of compactify with one of a multiple, well, maybe it's better to think of like, okay, take an SA, delete sort of one of the two components of the anti-canonical, you're left with some complex space. And then how, I want to say, okay, line bundles on that complex space that can extend to some compactification. It doesn't have to be the one you started with. So for example, on the Hopf surface, if you remove, you can actually trivialize away from one of the poles. So then you have a C times E sitting inside of your Hopf surface, would be that space that you're now considering compactifications from. Anyway, so I call that thing CMQ. And then the theorem, sort of bigger theorem, is that there also relates sort of functors from the wrapped, from these categories of line bundles to the partially wrapped and the wrapped categories, so that the following diagram commutes. If you take so if you take sheaves on your compact surface and then you kind of can restrict them to one sort of open subset, like away from one pole, away from the other pole, and then that sort of glues over the common open subset C star times E. So these are all restriction maps. Over here you have localization maps. Am I writing? Can you see my writing again? Yeah. Between these Fukaya categories. And then these blue maps are the mirror functors. So this actually gives you a hope of proving mirror symmetry using, maybe you want to say, okay, well, I want to express all of my coherent sheaves on my SA as sort of using sort of some cover of SA by objects that we understand a little bit more. So like these open sets away from the anti-canonical divisors. And then you would say, okay, well, similarly as I can understand a sheaf kind of like gluing over some C star times E, I can understand an object in my Fukaya category is just like something that lives inside something that has sort of the M0 K0 boundary conditions on one end, M infinity K infinity boundary conditions on the other end, and then sort of glues up over the common set, or sort of rather in this wrapped Fukaya category, they represent the same object, meaning like their image under these restriction or these localization functors is the same thing. So this diagram is like kind of a lot more powerful if you want to any sort of hope of understanding sort of a full mirror symmetry statement. I want to say this is some sort of like sheafy proposed proof. Okay, in our last 3 minutes, I want to just give the proof of that first theorem because I think it's really nice and geometric, and then I'm happy to talk about whatever else people want me to talk about. Okay, so so the proof of that first theorem, so remember this is just saying like, okay, the Picard group of the Hopf surface is going to be equal to, sorry, negative sign here, is equal, or sorry, there's a functor from that to the Fukaya category with the boundary conditions on both ends. And what this is going to do on objects, so recall that we had these objects LQK, or sorry, we had these objects like L lambda, lambdas in C. This is this line bundle you get from the representation of the fundamental group that sends sort of the action, acting by one to scaling by lambda. So I can rewrite all this in terms of Q. And I'm going to say, okay, well, so L of Q to the K So now I'm gonna say Q for this, the way I've written it here, Q is in R, and then K is also in R. It's going to send this LQ to the K to this object that I've kind of described in this graphy way again. So recall that Y is just equal to you know, R times S1 times S1 times S1. You take a section, so you specify the angular coordinates, and you say, okay, well the T angular coordinate is sort of changing, sort of in the same way we saw for P1. So this row of T is equal to you know, some cutoff function like that, or sorry, not cutoff, smoothed out step function, and then the phi T factor is just constant. So one can check that at when T is much less than 0, that this thing is just going to be TS0 negative K. So that satisfies the 1, 0 boundary conditions. On the other hand, these boundary conditions, on the other end, these boundary conditions say that your values have to be equal, right? Your phi T, phi S have to be equal. And you can verify that at the other end, this thing just looks like TS negative K. So you see that. And then what's happening here is like, you know, if you draw this, this is just a product Lagrangian, you know, it's a product if you, Lagrangian in the, if you split off the T phi T and the S phi S directions. And here's like an example of what it might look like if K is equal to like around 2.3 or something. Like you just kind of, you know, you start somewhere. So, you know, you start at 0, say that's 0, and you wrap sort of 2.3 times. So instead of this sort of rigid condition you had with the P1 where you have to only wrap an integer amount, you're now allowed to wrap sort of these non-integer amounts. And then I want to check, so I want to check like, let's just check Hom with like L0. So you say, so if I say H, I should have H star of L Q to K should correspond to intersections of L0 intersect LK. Note that when K is not in Z, L0 minus intersect LK is empty, right? Because this last coordinate is not going to be is not going to ever coincide, right? So and then remember that this is equal to X of so what I'm doing is, you know, L1, i.e. the structure sheaf O, or sorry, not the structure, you know, the trivial one model O, L1, LQK. So that's good. And now just when K is an integer, now you're going to wrap some integer value number of times. You're going to have, instead of no intersections, you are going to have intersections, S1's worth. And instead what you're going to do is sort of perturb this first guy, this L sub O, slightly. So that guy is going to be in blue. And then you see that you're going to end up with K plus 1 many intersection points sort of in this T phi T direction. So K plus 1 values of T where you have intersection points. And for each of those intersection points in the S phi S torus, you perturb and you pick up two sort of honest intersection points of your perturbed Lagrangian. So all in all, once you kind of keep track of Maslov indexes and so on, you see that this Hom space is going to be equal to this this sheaf cohomology group. So H star P1 O of K tensored with the cohomology of S1. Okay, and all in there, and yeah, pause for questions.
Thank you. See, you have a question from Sheil and then a comment from Mohammed.
Yeah, go ahead.
Hi, Abby. Thanks very much for your talk. So my question concerns the admissibility condition you wrote down earlier on Lagrangians that depends on this tuple of MKs on each end. So I see from that, so normally when I think about a Landau-Ginzburg model in the very traditional sense, I think of a map to C. And I see that what you wrote down is, you know, essentially the argument of that map away from a compact set. So you said, okay, the argument of this map to C has to be this thing that's equal to 0 away from a compact set and that thing on, you know, in that region. My question is, do you know if the mirror construction gives you a global map to C whose argument near infinity are these angles?
One up. You can cook one up.
You can always cook one up. I agree.
It would not be holomorphic.
Yes, of course.
So, yeah. So that's why it's kind of called yeah.
Right. No, it makes sense. I mean, certainly you wouldn't need to know what it does in a compact set to define the Fukaya category or anything, but I was just wondering whether I see. So you can certainly cook one up and maybe we shouldn't expect one.
Right. And in fact, that's what you're sort of doing. I mean, I sort of sacrificed any sort of motivation to like kind of get through the thing, but really what's happening is you can still see sort of two holomorphic disks. So let's just go to the Hopf surface case. You can really sort of see two holomorphic disks in your Hopf surface, wherever it went. Maybe I'll like, which pass through these sort of coordinate axes, right? So what I want to say is just like if you take sort of the product of two circles in the C star, so something like yeah, just like fixed norm 1, fixed norm 1, whatever, that gives you a torus. You want to think that of an SYZ torus. That thing still bounds two disks, which survive to which descend to disks in your Hopf surface, but now it doesn't have any well-defined symplectic area. So you're still sort of trying to count those disks, but it doesn't really make sense to have like a well-defined superpotential because you don't have any notion of area.
Okay, that makes sense. Thanks, that's helpful intuition.
Yeah.
Okay, Hiro says he has a jillion questions.
Yeah, I'm sure he does.
So I'll ask him I can ask them later too. And yeah, I have like 6, so I'm not gonna ask them all at once. But
we can also talk on Monday, Hiro. I think we're planning to do that. But I mean, whatever you think is helpful for
right. So actually, the first question I had has a lot to do with Roman Krotowski's question. So maybe I'll ask this one. So essentially the same thing. Have you thought about generalizing to Calabi-Ekmans? And then also the other question is, have you thought about what's a mirror to admitting an exotic complex R2N?
I have not thought about that second one, but it's a really good question.
Because that's like the most interesting thing about those Calabi-Ekmans.
Sorry, so mirror symmetry of Hopf manifold. So okay, so maybe I should just talk to Roman. I don't know what a Calabi-Ekman manifold is. A Hopf manifold, you can do this. This trick sort of works in higher dimensions too. So really, like what you sort of do then is say, well, a Hopf manifold can sort of be understood as I'm using Hopf to mean like a quotient of some punctured C to the n by a discrete group. There's a similar sort of game you could play where you say, okay, this can be understood in terms of log transforms. This log transform thing, like, okay, really, if you think about what I did was sort of like a procedure that can be replicated for any sort of generalized log transform on sort of a toric variety times an elliptic curve. So, take out a divisor, do some sort of log transform, and, construct some symplectic space where the boundary conditions reflect what you did, yes, that should give you the right answer in higher dimensions, and that can kill some of the Hopf manifolds. So I don't know what a Calabi-Ekman manifold is. So maybe.
Do you want to hear or?
Yeah.
So essentially, like, you know, what you can do is if you take a product of odd dimensional spheres, thought of as embedded in, you know, C to the blah, and you mod out by, you know, complex actions on each factor, kind of like you do to obtain the Hopf surface, you again get something, you know, over projective space whose fibers are elliptic curves. I think this is due to Calabi and Ekman. And if you remove the factors coming from each odd dimensional sphere, you get inside of this Calabi-Ekman surface some complex submanifold that's open, and it's obviously isomorphic to Euclidean space because you've removed the two odd sphere factors. And it turns out that almost all of these, I shouldn't say almost all, that many of these are exotic R2Ns, so they're not biholomorphic to a standard R2N.
I have not thought about that at all, but that's a really interesting direction, so thank you. More like the direction I have thought about is if you take some sort of elliptic surface where you do understand mirror symmetry. I mean, so all of this is kind of boring because, well, okay. Or it's not really boring, but rather like, you know, it's a very strange situation to have an elliptic fibration where all your elliptic curves are the same curve. Like, I mean, that can pretty much only happen if you don't have singular fibers, like if it's literally a product. So what you really want to do is some sort of more general thing where you take mirror symmetry for, like if you take mirror symmetry for something we understand, an elliptic surface we understand mirror symmetry for, like say like a rational elliptic surface, and then you can do a log transform to rational elliptic surface. Well, now you're in some like world of you know, something stranger, and you might hope to still be able to understand mirror symmetry for this new thing via your understanding of mirror symmetry for the original space. So all this just says like a direction that I'm particularly interested in is and it's why I sort of belabored the like logarithmic transformation thing, is sort of more general elliptic surfaces, and then what might get from this message. So yeah. So sorry. So Hiro says privately, this is not boring. I don't think it's boring either. I just meant from the point of view of complex algebraic geometry, like it's if you want to do sort of elliptic surfaces, like you really want to get beyond the sort of trivial case. All right. Other questions? I don't know what Mohammed had to say. So Mohammed. Yes, yes, yeah. I think I did answer that question already.
I think you have a question from Marco and then Zach.
Oh, sorry, Marco. I wasn't scrolling. Is there a guess for what a Landau-Ginzburg model to a Hopf surface that is not elliptic fiber could be? Not off the top of my head, but those things tend to be pretty boring because they're not going to have any sort of useful, there's not going to be any sort of things you can grab onto in their derived categories. So the thing about the Hopf surface is that it really has this family of elliptic curves sitting inside it, you know, parameterized by P1. In general, those things, the only divisor, the only like, you know, maps, the only curves that admits complex curves in it are just going to be sort of the two antipodal curves. So you're just going to have two elliptic curves sitting inside of there. So you're not going to have like many interesting objects in your derived category, or at least anything that I can sort of get my hands on by these methods. So to answer your question, sadly, is no, I don't really have a guess. Yeah. Okay, and then Zach, I mean, do you want to read your question out loud, Zach, or I can read it?
Sure, I can read it. is there a nice relation between what you're doing for the Hopf surface and the FLTZ mirror to c squared minus the origin?
That's a really good question. I don't know because I don't know the FLTZ mirror to c squared minus the origin.
You take a torus.
Mm-hmm.
So I'm going to give you a skeleton on that torus. Take
Mm-hmm.
two circles,
Mm-hmm.
the two like standard circles on it. You take the one-sided conormal to each of them.
Mm-hmm.
So that's
yeah, I see. So you can definitely do it. Let me. I mean, I can. That's a really good question. I have to think about it. I don't know. I mean, I guess one hopes it's sort of like you're just kind of quotienting whatever FLTZ mirror you have, which is like not going to be quite right. But like sort of, you have a quotient on one side, you have a quotient on the other side. But it's not. I don't know. I would have to think.
okay.
Okay, well,
So one thing I want to say, sorry about that question, is like I wonder, I mean, c squared minus 0, like you sort of can extend any holomorphic function on that to c squared. So I wonder like how you would, if you want to just consider like on the complex side, like I'd have to think. I mean, you'd have a bunch of like weirdo analytic sheaves, but somehow like those would be kind of hard to understand. So it'd be kind of hard to think about what the mere symmetry statements would be like. Okay. Yeah.
let's thank Abigail again. And we'll move on to the informal discussion now. So I think we usually stop recording here.